here. All right. So once you bring this one, this you have triple bond is more than enough. So this one you have to come to this side. So you have this particular structures. So that you can say you have this to this minus single bond n, triple bond what n. So this one is going to carry plus. Are you okay with that now? So it's going to carry plus, then the lone pair of this one will be like this. So this is how it is. So let's just do more. Okay, so that is that about the resonance structure. So that's that about resonance structure. But let me quickly do a quick recap on one slide like that we have here. Alright, so I've explained the rules guiding resonance. So for resonance, this is the ability of electron in the conjugated system to move in between atoms in a molecule. So resonance results in oscillation of electron between atoms within an ion or molecules. So no definite description of valence bond, alright? So electrons shift in resonance, alright? When writing structural resonance structures, curve arrow that allow us to progress systematically, this is the curve arrow, full-headed arrow. If this half arrow like this, you know what is going to happen now. That is a single electron. I've explained that earlier before. One resonance symbol to another used to know shifting of electrons. The relative position of the nuclei of the atoms are maintained. Atoms does not change position. I told you atoms will not change position. Only the bond that changes position. I've explained that. Only electrons are delocalized or shifted. Only pi electron or shared valence electron can be shifted to. Alright, so yes, let's quickly do this. I want us to finish this one first. So the it's only pi electron that have been delocalized and being shifted. It's only pi electron that have been delocalized and being shifted. Electron shifts are purely artificial because electrons do not truly shift but are delocalized. There are two types of arrow used to the electron shift. Alright, so that is why you have to take note of that. So for example, we have C double bond C, right, to X rather. Alright, so if you move full arrow to this side, so you are going to have something like C plus. Look at the arrow I'm using. That is resonance structure arrow, both arrow head. So you have C plus, then X minus. Okay, so if there's this, so half arrow. So both of them we have radical. We have radical here, then radical here. Are you okay with that? So that's what we are trying to see. So you have radical here, so that is it. So type of structure that show resonance. Type of structure, conjugated system with double bond or triple bond can show resonance. Conjugated system with double bond or triple bond can show resonance. I've explained that. Conjugated system, double bond or triple bond can show. For example, this is a conjugated system, right? The conjugated system, it can show something like resonance, right? This is also conjugated system. You know why this one can do like this? Okay, it can move, so they can show resonance. Here you get now. See this one too can show resonance. This one will come down to this side. This one will come here. White double bond there will come here. So you can have something like so. Isolated system and cumulative system will not show resonance. Isolated will not show resonance. What do I mean by isolated? For this guy, they will not show resonance. So cumulative or commutated, this guy will not. They will not, because there is no space to move the electron to. You can actually move it, like you can move it so that you can have this minus here, then plus here. Are you okay with that? So that is all right. So let's do an example here of Okay, I've explained that butadiene. I just did an example here. So structure with double bond or triple bond in conjugation. So an atom having a pi orbital or a p orbital. So let's say there is a compound that has a p orbital, and that is they can expand their octet. That was what I was explaining. Group 3 element, they have p orbital, contain 2 electrons in it. For example, let's do this. This one can, this is 1, 2. Compound structure or double bond, p orbital. The atom that has p orbital is connected to a triple bond double bond. For example, look at this H2C double bond CH to Cl. Alright, you know Cl is having this. Alright, so you can have the movement of this to this side so that this guy can come here. So then you now have what? Now H2C minus, okay? Then CH to CH double bond, see what? Cl. Are you okay with that? So they can expand their octet. Okay, so that is that. With p orbital contain just one electron in it, just one electron. I've explained that. With p orbital which is empty, so you can have p orbital that is empty like CH to CH. So if there is no p orbital that is empty, okay, like for example this one, the p orbital here is actually what? Empty, because there is no double bond close to this side. So this one can quickly move this. All right, are you okay with that? So that you can have this, both of them can have H2 CH, sorry, CH2 plus Cl minus. So that is hyperconjugated system. Hyperconjugated system to free radicals and so on. All those ones can read them out. Carbon with free H, so an alpha to sp2 hybridized. Okay, so let's say you have something like R to C to H to R to CH double bond CH2. Right, so resonance can occur so that you have R to C double bond CH, then R to CH2 minus. What does this mean? So this guy can come here, while this one will move. So that is what they have here. So it's just like annihilation of hydrogen. You are moving of hydrogen, so you now have H plus. So that the system will be neutral. If you don't do that, the compound is not complete. Carbon with free hydrogen alpha, so things like that occur. Rules governing resonance. The relative position of nuclei must be maintained. We've done that. All atoms must be part of the resonance. Okay, you can rules govern. Okay, canonical forms must be the same number of unpaired electrons. So what you start with must be what you end with. Are you okay with that? So that is that. That is what I was all about. Rules. You can just read off. Identify the most stable canonical. How to identify the most stable canonical structure? How to identify the most stable one is it will depend on the major and minor contributors. So how this is very important. How to identify the more stable canonical structure. Okay, so we talk about this. Alright, so how to identify the major and stable canonical structure. Alright, that will be our next class now. How to identify the most stable and canonical structure. So let's pause here for this, so we move to the next one.